Okay, continuing on today with our Laplace Transform playlist, we have here an example of an inverse Laplace transform. We want to find the inverse Laplace of minus 12 over s squared plus 4s. So just a quick recap of what we went over for inverse Laplace transforms in the previous video. What we're doing here is we just want to do the process in reverse. So we've been doing previously a bunch of Laplace transforms. So what we want to do is if we could recognize this as one of our formulas in the table, then we kind of go backwards and put this back into a function in terms of t. Now the trouble with this specific example is I don't recognize this as any of our formulas in our Laplace transform table. So I don't know, so just by looking at it, I don't know quite what to do. It's almost like sine, right? Like sine, if we didn't have this s here, s squared plus 4 would be like sine of 2t maybe with some constant. But that's not what we have here, so we need to do something else. So in a case like this, I actually know two ways we could factor the denominator and then do partial fractions. Or we could complete the square and then see what we have from there. I'm actually going to do both methods. So to start with, we can actually factor this, just factoring out an s. I can write this as s times s plus 4. And when I rewrite, I'm actually going to take we can take the minus 12. We can factor the constant up front, because the same property we had for Laplace transforms also works for the inverse Laplace transform. So now we'll just have a 1 here in the numerator, and then we'll have this s times s plus 4. And again, this still doesn't look like anything I have a formula for, but we can do the partial fractions on this. So how am I going to set this up? So to set this up, we'll write it over here, and we can actually use the cover-up method on this. So we're going to say our fraction here, we're going to set it equal to a over s, and then the other part will be b over s plus 4, and we just need to solve for a and b. So for the first part, we'll set s equal to 0, but then we'll cover up the s and plug it in here. 0 plus 4 is just 4, so for this fraction, we're going to have 1 over 4. That's going to be our a value. Then doing the same thing for the second part, to make this s plus 4 equal to 0, we want s to be equal to minus 4. Cover up that, plug it in here. So we're just going to have 1 over minus 4, and so this is going to be for b, it's going to be minus 1 over 4. So now we can take this, we can plug it back in for our Laplace transform, so copy this down. So for this first part, we're going to have just 1/4 over s. And then for the second part, we're going to have minus 1/4 over s plus 4. But again, I can split this up on the plus sign and factor out the constants here. Okay, so we'll do all that kind of in one step. So factoring the 1/4 out and multiplying it times minus 12, we're going to have minus 3 in front, and then we'll have the inverse Laplace. This will just become 1 over s for our first one. And then for the second one, we'll multiply minus 1/4 times minus 12. And we'll get, this will be a plus 3, and then we'll have inverse Laplace, and this is just going to become 1 over s plus 4. But now at this point, we can actually use formulas, because now this has become familiar, what we have here. So for this first one, we can use the formula. We'll have the Laplace transform t to the n. When n is an integer, this is just going to be n factorial over s to the n plus 1. And then for this other one, we have a familiar formula, Laplace of e to the at. This is going to be 1 over s minus a. So now for this first part, bring it down to minus 3. To get this from this equation, just notice we would need our n to be 0. Then we have 0 plus 1, we have just s to the 1, which is this. And then we have 0 factorial, which is 1. So actually we have t to the 0, or just 1 here. So for this next one, we'll use this formula here. Now in order to get 1 over s plus 4 out of this, what we would need is we would need a equal to minus 4, right? Because then we'd have 1 over s minus 4, which is the same thing as 1 over s plus 4. So if a is minus 4 using this formula, this here is going to be e to the minus 4t. And so we'll just write this in as our solution up here. We're going to have minus 3 plus 3 to the e minus 4t. Okay, so I'll keep this solution on the board. We'll go on to our second method and see if we can come to the same solution. Okay, so for my second method for this, what I want to do is complete the square. So I can take this and take half of the coefficient here on the s. So we can have s plus 2, square that. That's going to give me s squared plus 4s plus 4. We don't want to change it, so I'll just subtract off of 4. And so now what I'll do is rewrite this, but again, I'll bring my minus 12 out front. And then we're going to have, this is going to become just 1 over s plus 2 squared minus 4. The minus 4, I'm actually going to write this as 2 squared. And now at this point, this isn't really any one formula in our table, but it's pretty close on a couple of things. Let's take a look. So First of all, we have this formula for, let's see, we'll use sinh of AT. And that formula is going to be A over S squared minus A squared. So we have the denominator right. We're saying that here our A value would be 2 in this, but we don't have a 2 in the numerator. But fixing that is actually really easy. I can just multiply by 2 to create it here, but then I'll just divide by 2 out here so I don't change it. And so now at this point, this is really close to our formula, but not quite, because we still have this s plus 2 here. So we have some kind of shifted function. Well, we have something for that. But generally, when we have one of our common formulas shifted, we can use this formula e to the at times f of t. This is going to be just big F of s minus a, so shifting the Laplace transform of just of our f of t function. So in order to get s plus 2, the shift we want would be minus 2. Let me just change this a so we don't confuse it with this other a. So let me just we'll write this formula as e to the bt, and we'll write this in as a b. So now here, if we have a b value of, say, minus 2, then plugging that minus 2 in here, we're saying our result is shifted like s plus 2. So what I can do is actually put these two formulas together. We can look at the Laplace of e to the bt sinh at. So then we can actually just take this formula and shift it and write it as a over s minus b squared minus a squared. And that's exactly in the right form for what we have here. So let's see if I can put all this stuff together. So first, this minus 12 over 2, I can write this as minus 6. Then taking this and going backwards, but we have our a and b value. B is minus 2. A here is going to be 2. So putting it in here, this is going to be e to the minus 2t for our b value. And then this is going to be sinh of a equals 2, so sinh of 2t. And now this would be a fine answer. The only thing is this looks nothing like what we have here. But the nice thing is we can use the definition of sinh and see if we can work with that and make it look like that. So let's see, we'll have minus 6 e minus 2t. Definition of sinh is going to be e to the 2t minus e minus 2t all over 2. So then let's just simplify. So minus 6 times minus 2, this is going to give me a minus 3 in front here. So e to the minus 2t times e to the 2t, e to the 0, or just 1. Then multiplying it for this last term, it's going to give me e to the minus 4t. I can just distribute in this minus 3. And so for this solution, we're just going to have minus 3 plus 3 e minus 4t. And that's exactly what we have right there. Okay, so there you have it. Interesting inverse Laplace transform with two methods. Thanks everyone for watching. Have a good day.